networks, if that's possible, compared to last time. You will recall that at the end of last lecture, we were basically here. And we had, at this point, designed this neural network to train it to perform a function which you might think of as a probabilistic XOR. It has two inputs. Its output has this probability distribution. You see it's kind of a lot like an XOR, except it's only probabilistic in its output. And so we agreed that just like logistic regression, we would train it to minimize... Oh my goodness. Nice. You got so enthusiastic. I killed my mic. Okay, so we decided we're going to train it just as we do logistic regression to maximize the likelihood, the conditional likelihood of y given x in our training across the summed over all the training examples. And we got to the point where we had designed the network with two rectilinear units at the beginning, with that this activation, the rectilinear activation function applied to basically a dot product of the input with the weights of the individual units. And then the final stage of the network would be a logistic function, which of course you're very familiar with. And we had calculated these values for the network. So what we need to do next is, now that we've executed the network, we can see what its prediction is for this input. Its prediction is that the probability that x equals 1 is 0.53. So now what we need to do is look at what the training example says that y actually is, and then get the gradient, that is the set of partial derivatives of our cost function with respect to all of the parameters in the network. How many parameters are there in the network? 9, right. So we have to get it with respect to all 9 of those parameters. Okay, so here's the first of those. First we have to start. Remember, our cost function we agreed was just the conditional likelihood, the log of the conditional likelihood. And then in order to be conventional, as if deep networks were old enough to have a convention, we use the negative log likelihood and say we're going to minimize it. Okay, so now what we have to do is derive the derivative of that cost function with respect to each of the parameters. And instead, what I'm going to do is first get the derivative of that cost function with respect to the output of the network. The reason I'm going to do that is, as we talked about at the end of class, we're going to use the chain rule of calculus to compute the derivative of j with respect to any given parameter in terms of the derivative of j with respect to something else, and then the derivative of that something else with respect to the parameter of interest. And as we'll see, this is going to make a very efficient way of calculating the, how many was it? 1, 2, 3, 9, yes. All those partial derivatives that we need, because we're going to be able to reuse calculations that we've made along the way. Okay, so so in fact what I'm going to do is I'm going to get the derivative of j with respect to, and what I'm going to do is do this with respect to each of the parameters, but also each x sub n sub I, and also each g sub n sub I. Remember, g is just the internal computation inside the unit, then we apply the activation function to it. And it turns out that by getting all of these, I'll set up a system where it's easy to calculate the next derivative based on the derivative I've already computed. Okay, so the first one is, let's look at the derivative of the output of the network. the derivative of j with respect to the network output. And of course, here's our loss function again, just copied straight from the top. And there are basically three magic formulas. If you don't remember all of calculus, there are basically three key formulas from freshman calculus that we're going to use. One of them is this, that the derivative of the log with respect, natural log with respect to z is 1 over z. Okay, so we can use that here. In fact, that's just what I've done. The derivative of this expression I can break into the sum of terms. This term becomes y times the derivative of the log of x with respect to itself. So now I invoke this simple formula, and that gives me 1 over x3 sub 1. So this term becomes y times 1 over x3, 1. This term becomes 1 minus y times the derivative of this with respect to x3, 1. So here I actually use the chain rule already. What I do is I get the derivative. I take the derivative of log of 1 minus x3, 1 with respect to what? I'm using the chain rule, so I'll do this, because now I can use our well-known formula, and then I'll multiply that by the derivative of 1 minus x3, 1 with respect to the thing I really care about, which is x3, 1. Okay, so simple use of the chain rule here to re-express the derivative of this with respect to x3, 1 lets me invoke this trick. So now I have 1 over 1 minus x3, 1 times the derivative of this with respect to x3, 1, which of course is just minus 1. So that's there. Okay. So very straightforward calculus as long as you remember this formula and the chain rule. So the calculus in this course is actually pretty straightforward. It's basically the chain rule and using it repeatedly. Okay, so now we know the derivative of our cost function with respect to the output. And if I now tell you the true y for that input was observed to be 1, the training example had this input and was labeled as y equals 1, which would make sense for an exclusive OR. So this was a highly probable output. Now, what's the value of the derivative? Right. This term is 0 because 1 minus 1 is 0, so we ignore that. This is the term we're going to use only in the case that y equals 0. But since y is 1, we now have minus 1 over x3, 1, which we already know is 0.53. Okay, so this derivative is 1 over minus 1 over 0.53. Okay, so that's the derivative. Yes?
Could you explain why we go from log of the probability to log of x3, 1? Like how do we go from the log of the probability to log of x3, 1?
Oh, how do we go from the log of the probability to log of x3, 1? All I was doing was, I need the derivative. I mean, j is up there we agreed. And this rewriting of it is simply the if statement that we've talked about a few times. So if y equals 1, we're going to use this. If y equals 0, we're going to use that. So when we take the derivative, it comes out as we just discussed, except that we need the derivative of this term with respect to x3, 1, and I don't know how to do that directly. So instead, I use the chain rule. And I say the derivative of this with respect to x3, 1, which is what I want, it is determined by the chain rule by taking its derivative with respect to something else that I make up. And I'm going to make up this because now I can say z equals 1 minus x3. And so now I know the derivative of this is just 1 over whatever z was, 1 over 1 minus x3. So that's how it comes through. And then the derivative of this, as we said, is just minus 1. So we get that product. So that's where the probability gives us the x3 one. Okay, so now we know the derivative of our cost with respect to the output of the network. What do you think would be the derivative with respect to this value? Well, for that, we're going to have to remember how we computed x3 from g, but that's easy. You remember, that's just the sigma function, right? The sigmoid unit, just like the logistic regression formula, takes its inputs, does a weighted linear sum of the inputs in terms of the parameters w and b, and then whatever that weighted linear sum is becomes the input to the sigmoid function, shown up there, f3, the sigmoid function. And g is just that intermediate term, the thing that's going into the sigmoid function. So if we want the derivative of j with respect to g(3,1), this piece right here, again, I can use the chain rule. And this time I'm going to pick something I already know. We just computed this. It's minus 1 over 0.53. And so I can use the chain rule to say, well, the derivative of j with respect to g1 is just that derivative I already know times the derivative of x with respect to g. And what is that? Well, here's formula number 2 that you should remember from for this course, which is if you ever have the sigmoid function, the function we're using here for f3, then a wonderful property of this function is that the derivative of its value with respect to z can be written this way. It's just the output of the function times 1 minus the output of the function. It's pretty cool. Okay, so in this case, that means what? Well, it means that since the output of g is x3, that's what the network is doing, it's just x3 times 1 minus x3. That's what the output of sigma is. So it's actually a very straightforward step. And now you can tell me what is the value of this. What's the value of this derivative? I'll give you a hint. This one was minus 1 over 0.53. So what's this? Well, again, we know the value of that. We calculated it during the forward pass at 0.53. So we just have to multiply that by 0.53 times 1 minus 0.53. Now we know the derivative. This is the derivative of our cost function with respect to g3. So you see what we're doing here. We're calculating them by getting the formula. Of course, you get the formula when you derive the algorithm. You build that into your code. But then for any given training example, if we're doing stochastic gradient descent where we calculate, we pick a random training example, get the gradient with respect to that, and update our weights, then you can see how simple it is to get the gradient, which is simply the set of all these partial differential functions that we want. But the ones we want are, as you said, these 9, the ones that are actually the parameters of the network. So let's go one more step. Next, I want the derivative of my cost with respect to, let's say, this parameter here. How am I going to get that? Right, so now all I have to do if I want the derivative with respect to this, again, I'll use the chain rule. I'll say that's just the derivative with respect to G3 times the derivative of G3 with respect to this weight. And that's easy to calculate too because we know it's just this function that depends on the weight linearly. Okay. And in fact, it's just the value of x, right? Because up there I've written G3. I'm looking for the derivative of this with respect to this weight. Up there I wrote it in matrix form, but if I wrote it out in simple arithmetic form, it would look like W1 times X1 2 plus W2 times X 2 plus B I lost my indexing. I'm calling this X3, I'm calling this X2. Okay, that's good. Good, so I have X21 and X22 are the inputs to this unit. If I express that just as without vector notation or matrix notation, it's just this. So if I ask you if that's G3, what's the derivative of this with respect to the first weight, W1? Obviously, the derivative is just X21. So there it is. In fact, for the ith weight, it's just X2 sub I. In this case, we have two X's. Okay. So again, it's a very trivial computation to get this, given that I already calculated that other one. If the derivative of our cost with respect to G is minus 0.47, this derivative is just minus 0.47 times whatever X2I is, which is 0.2. Okay, so you should get the idea here. What we're doing is really a kind of dynamic programming where we're sharing a lot of internal computation and we're calculating a sequence of partial derivatives that make it just trivial to calculate the next derivative that we want in the sequence. Of course, the only ones we really want are with respect to these 9 parameters that we have. But it's worth the extra effort to just go through everything. It makes the coding easy. Because the way you'll implement this, if you do it, is for every kind of unit that you use, like a sigmoid unit, you'll actually calculate what is the derivative of this with respect to this. Or if you change the activation function to something else, you'll want to actually chop it into derivative this and then this. Okay, so we just keep doing that, and then we can get the derivative with respect to the next thing, the X2s, the second layer of X's, which again are just with respect to G3 times G3 with respect to X. The interesting piece here is where we get to the derivative with respect to GI2, because G2, that's our first layer of the networks that's producing the X2s. And remember, that is X2 depends on G2 by this function F2, the max of 0 and Z. That's the rectilinear unit. And so if you think about what's the derivative of the output of a rectilinear unit with respect to its input, so if this is X and this is F2, or maybe I'll just call it Z to not confuse us, and this is F2 of Z, and this hinge here is at Z equals 0, then the derivative is 0 over here, right? The slope is 0 here, and here the derivative is 1. right? The derivative of f of z equals z is just 1. The derivative below 0 is just 0. So I actually have an if statement in here to calculate the derivative of j with respect to gi. That's because it's depending on the derivative of the output of that first unit with respect to its internally computed g sub 2. And so this part actually becomes, well, if g is below 1, then the derivative will be 0. Otherwise, sorry, if it's above 0, then it'll be 1. Otherwise, the derivative will be 0. But again, it's a simple calculation. So as we get down to the bottom of the page, we've calculated every single one of the derivatives we need, all 9 of those, plus a few extras just to make it easy. So that's the whole idea of backpropagation. You can see now why it's called backpropagation, because you're propagating information about the derivatives back from the cost function to the output of the network, and then back through the network all the way to the beginning, all the way to the initial weights that are directly working on the inputs to the network, which are these. Okay, so now we've got all of the derivatives. In fact, here they all are, calculated out number-wise. So these are the ones we just got, the derivative of j with respect to x3, the output, all the way down to here. And so now the update is very simple. What do we do for gradient descent? We add to the current parameters the vector of parameters. We add the vector of partial derivatives. Or put another way, for each individual parameter we have, I'll use theta to mean the ith parameter is theta I. Could be one of these 9. But for each of those parameters, we're just going to update it by adding into it the derivative we calculated, negated, and multiplied by some positive learning rate. Why negated? Because we want to go downhill, and the definition of derivative is if I take the derivative of j with respect to theta, and I get a number, what that means is if I increase theta, this is the amount I'm going to increase proportionally j. And so since I want to decrease j, we're trying to minimize the negative log likelihood. So that's where the minus comes in. And then this thing, eta, is just some constant that we make up. If we make it up too small, it takes a long time for gradient descent to iterate to get to the answer. If we make it up too large, then we might go right through a bottom of a hill of a valley and miss the minimum. So we want it low enough, small enough that we can take small steps, especially when we're by the minimum that we're settling into. We don't want to bounce back and forth across that valley. So it's kind of an art, not a science, to pick the right value of eta. And there are many algorithms for variants of gradient descent. Some of the better ones actually adaptively change the learning rate over time. Starting out with a big value, so you can take big steps, and then over time just shrinking the learning rate so you take smaller steps the further you go. Okay? Questions? All right, so we can do it, in fact, on our data, since, as you can see, I had an Excel spreadsheet to make sure I got the arithmetic correct. So we could just take these derivatives. Let's pick a value of eta to be 1 to make it simple. Then what's the updated value of, say, this weight? If I use an eta of 1. Right. Now it's going to be 0.19, I hope, on the next slide. Because if we're using a learning rate of 1, then all I do is subtract from this the derivative of j with respect to it, which is minus 0.9. So if I subtract minus 0.09 to this, I should get 0.19. Okay, and similarly, basically I can do a matrix, component-wise matrix addition of these and just be done, or subtraction. And similarly, you notice the way we've set this up, it makes it very clear that for an efficient implementation, if we have a programming language or a machine that does matrix operations very efficiently, then it's very efficient to do both the forward and the backward propagation as very straightforward matrix operations. So this one really to get to here is just the dot product of this column vector with this matrix. Similarly here. And then now I'm doing an element-wise addition to each component of those once I get the gradients. And the gradients themselves, you should see, are very efficiently gotten. So it's pretty fast, pretty efficient. Yes?
Are computers able to know when the function that you're using is not the derivable?
The question was, are computers able to know whether the function you're using is continuous or not? No. And so when you write the program, you have to do the reasoning about how you're going to calculate that derivative, and you have to write the code to calculate the derivative. So that's the level that separates the derivation of the algorithm from the actual code that implements it. What you'll do is you'll calculate all these derivatives that I talked about, all the formulas for the derivatives before you implement the code. And then when you implement it, you'll build those formulas directly into your code. And so that way, you've already pre-solved all the questions about what are the derivatives. Okay, so we can do this, and in a spreadsheet it's even straightforward to do that. And so sure enough, we get a 0.19 here, and similarly other values updating these parameters. And that's one gradient descent step, more properly one stochastic gradient descent step, because we're using just one training example here instead of all of them to calculate the gradient. Okay, and then suppose the next training example again has a 1, 0, and I'm not telling you yet what the y is, but now to start training on that, the feed-forward calculation of what the output would be now is shown here. And then we would recalculate this table of gradients and update again and just keep iterating on different training examples that we get from our training set. And you know, here you can see that we used a rather aggressive value of eta. It's kind of not usual to use 1.0. It's more common to use numbers like 1 out of 100th. 0.01 is a more common value for this. But I used the 1 just to make it more obvious what was going on. And you can see that now we've taken a pretty big gradient descent step. And now, for that example which previously we saw in the training data had a y equals 1, now the probability the new network assigns to y being 1 is now 0.065, or sorry, 0.65 instead of 0.53. So it's taken a gradient descent step that makes it better fit the training example from which it calculated the gradient. And that'll just keep happening. Of course, every time we pick at random a different example, we might not always get a 1, 0. We might get something else. Okay. Now there's another kind of interesting thing that happened here. Some of these partial derivatives are all zeros, like 4, 5. The majority of our partial derivatives turned out to be 0. 5 out of 9. You might view that as kind of disappointing, since obviously these are randomly initialized parameter values. So how could that be? What causes a 0 gradient here? Right, so one thing is the rectilinear activation function, right? We said that if you're in the flatland part of that, just by definition, it's 0. But also, going forward, a number of the values that we were computing, well, this one also ended up being 0. And so when we were calculating the derivative of this weight with respect, the derivative of our cost function with respect to this weight, the formula tells us the value of that derivative by the chain rule is the derivative of the cost function with respect to this times this value of x, which happens to be 0. So we can get 0 derivatives if the data, if the x value is 0 here, or if we happen to be operating in the region where we're in the flatlands of the rectilinear cost function. And so one way to think about this is those rectilinear units have the property that they kind of hide part of the network from updates if you happen to be in the zeroed out portion of that. Like if we had a much deeper network that kept going and had other units, layers of units feeding into this, all of the derivatives behind let's see, will it turn out? I have to be careful what I say. But the bottom line is that we can screen out changes to parts of the network because of these 0 derivatives. And it's kind of one of the interesting properties of using rectilinear units. In a way, what they do is they kind of parcel up the Euclidean space of x inputs to the network into regions that can be screened out depending on whether we're in the flatlands. And whether or not we're in the flatlands is learned because the reason this thing's a 0 is that these parameters made this be a negative number, and therefore the value was 0, and so is the derivative. So it's kind of that the parameters learned by the network let you decide which parts of the x space are going to be screened out. That's one kind of intuitive way of thinking about it. Okay? All right, so that's a rather detailed example, but I think it really is, it's a great way to learn this stuff. You really have to go through an example at this level of detail. In fact, you will in the homework assignment that was just handed out this week, again go through in this level of detail. And I urge you to do what I did here, which is just build up your own little table of values. It makes it easy to keep track in one place of all the things that you need. But you should be very happy, because I'm just envisioning a little bit into the future when you're graduated and you go out to interview for a job, and your interviewer asks you, well, do you know anything about deep networks? You're going to be able to say, would you like the maximum likelihood version or the map estimates? Which cost function are you talking about here? Would you like a negated log likelihood, sometimes referred to as the loss, log loss? And then if they're on the ball enough and they say, yeah, I want the maximum likelihood, then you're going to say, well, let's start with the fact that maximum likelihood here would be maximizing the correctly assigned probability mass, or equivalently negating the log of that. And you'll be able to actually honestly say that if you worked with these things, you know how to derive them. And as you probably are aware, there are very few things that are in higher demand these days than expertise in machine learning, and then within that, very few things that are in higher demand than expertise in deep networks. So this is really worth learning, and not just for the fun you'll have during your interview, but for the career that you'll have after that. But I want notes and letters from you when you get those interviews when that happens. Okay, so here I've just gone ahead and done another update, and you can see what's happening. Okay, so end of detailed example. A different example I could have chosen, which is a very common kind of network, or in fact was a very common kind of network up until about 10 years ago, is the one that we started talking about. Remember when we were doing the speech, the vowel sound recognition in terms of speech formants? That network, in fact, was 2 layers of sigmoid units. Kind of like what we did, except that we had first layer of rectilinear units followed by sigmoid units. And here is the entire definition of the back propagation algorithm in a small number of simple formulas, just to show you when you actually work this all out, how simple it is. So this, as the title says, is the algorithm for a 2-layer, fully connected sigmoid unit network where we're trying to minimize the sum of squared errors. So here, instead of treating the output as a probability, which we did in the example we just went through, here we're treating it as a regression problem where t is some real valued target output. We have a number of them, and so for the ith output, t sub I is the target output. And O sub I is the training example. So T is what the network produces at the ith output. O sub I is what the training example says it should have produced. And when I use the D, I mean the whole vector of these for all the i's. So basically, we want to sum over our training examples and over the outputs the squared error, the difference between what the network outputs and what the training examples said it should have. And as we mentioned when we talked about linear regression, we can think the sum of squared errors, if we minimize it, is actually equivalent to minimizing the negative log likelihood if we assume we have zero mean Gaussian noise added to the outputs. So there's a sense in which minimizing the sum of squared errors is the same as maximizing the likelihood if we assume a particular, make a particular assumption about the noise in the data is generated by a Gaussian zero mean random addition to the observed y. That's a detail. But what's not is the algorithm. It's very straightforward. Basically, it says input the training example and calculate the outputs, do the feed forward part. And then for each of our output units, we're going to calculate this quantity, where this is basically the difference between what the network outputs Oh, I see. I'm sorry. I got my T and my O backwards. O is the observed unit output in the network. T is the target training output. I got my O and T backward. But anyway, this is just how far the network was off from the correct answer. And then what do you think this term is? Does that look familiar? That's the output of the network. That's the derivative of the sigmoid function, right? We were just talking about that. So we calculate this quantity. It turns out that that quantity is the derivative of our cost function with respect to the kth g applied to its input. So if we're on the kth output, if we're on the kth layer of units or the kth unit in the network, this is the derivative of the cost function with respect to that internal value before it goes through the activation function. So that's what it is. And then for each hidden unit, so we do this for each output unit, for each hidden unit, we do this. And now you can see something we didn't see before. Because in our other example, we never really had the case where a hidden unit feeds two different outputs, because we only had one output in our previous example. And so here what we're trying to minimize is the sum over all of our training examples of the sum over each of the outputs of the network of the squared error. And so here for the hidden unit H, one of, say, the red circled one, what I need to do is take its output times 1 and minus its output. That's the sigmoid function it's using. But now what I'm taking are these deltas up here, weighted by the weight value that goes from this hidden unit h to output number k. So it ends up being a weighted linear combination of these output values. The reason for that you probably can see is just that if we're trying to get the derivative of the red circled unit with respect to our cost function, which takes into account all of those outputs, then the red circled unit contributes to each of those output values, and therefore the derivative of the cost function with respect to h is the sum of many contributions, one for each output. So in general, whenever you have an outgoing branch and you calculate these derivatives, you end up summing the contributions from each of the different paths from it to the cost function j. Okay? So that's one thing that this general algorithm illustrates that we didn't hit in our particular example. And then once we have those, we just do the gradient update. For each weight from unit I to unit j, we take the old one and add in, again, our derivative. We don't have a minus sign here just because the delta has the minus sign built into it. Okay, so it's the same thing. And you can see that, when you put it all together and work out the formulas in advance for the derivatives, then the algorithm itself is actually quite straightforward and iterative. Okay, so that's all I want to say about the details of backpropagation, although we'll get to cover it more in the homework. I do want to point out that there's an industry of research and development on better ways to do gradient descent for particular kinds of applications and particular kinds of architectures. In the literature in this course, we're not going to have time to go into all these, but we did talk about the difference between stochastic and batch gradient, using all of the training examples to calculate the derivatives versus just one example at a time. I would say that for large-scale neural networks, by far the most popular thing is stochastic gradient descent, because it's a lot faster than going through large amounts of data and calculating a more accurate gradient. To take a small correct step, it turns out in practice to often be much better to take a number of not quite as correct small steps for the same amount of effort. Also, many people use mini batches. That is, if they have 100,000 training examples, they don't necessarily compute the gradient from just one of them. They might use mini batches of size 10 or size 100. So there's a whole spectrum on that trade-off between cheap computations of approximate gradient versus expensive computation of correct gradient. Momentum is something that is frequently used. That means when you take a gradient descent step and the gradient points you in a certain direction, you don't actually go that direction. What you do is you go that direction plus the direction you went on the previous iteration. You take those two vectors and add them together, some weighted combination. So it's called momentum because if you think of gradient descent as going down a hill, the direction you were heading on the previous iteration constrains the direction you're going to go next. And so it's sort of like you tend to keep going in the same direction if you use that kind of momentum. And again, very few of these things have hard theory behind them, but momentum was introduced as a mechanism for getting through local minima. So if I have a surface like this, maybe I want to get all the way here. If I just did momentum-free gradient descent, once I hit the valley, I would stop. But if I have momentum, I might keep going and get over the hill. It's very heuristic, but that's an idea. Gradient clipping just says if you have a really big value for the gradient, just clip it down to something smaller. Batch normalization is really interesting. It's a technique that is built on the following observation. In many cases, if you have a network with many layers, the gradient, the derivatives, close to the output of the network tend to be larger magnitude than the derivatives early on in the network. And you can see from the chain rule that what we were doing there is we were multiplying the early gradients by the next later gradient. And if those gradients tend to be, let's say, less than 1, then you can see that more numbers you multiply together that are less than 1, smaller and smaller they will get. And so there's this kind of empirical phenomena that in many networks, what happens when you do gradient descent is that the output values change a lot, and then further into the network, earlier in the network you get, the smaller the changes. And batch normalization is a technique to combat that effect, to say that, no, we're going to, for example, we might normalize for every layer the magnitudes of the gradient there, of the partial derivatives there, to be of the same magnitude at each layer. So if we have tiny gradient steps early on in the network, we're going to increase those so that they have the same magnitude as the output. Dropout is an idea that says, it's kind of a crazy idea, but is remarkably useful, and it does have some theory behind it. But what it says is, when you are training your network and you're doing the backpropagation update, or you're doing the processing of each training example, randomly throw away at random a certain fraction of the nodes in the network. So it's like if you have a network like the one on the previous page, it would be like with dropout, we might pick a number like 30%. We're going to throw away 30% of the nodes in this network each time we take a gradient descent step. We randomly choose 30% of those, throw them away, pretend they don't exist, and calculate the gradient for that lobotomized network, update just the weights that are in it, and now bring back in the old weights and nodes that we were ignoring and repeat. It sounds crazy. And when I first heard this idea from Gent Hinton, I thought he was crazy. But it turns out to be a very effective and widely used technique. And there's some interesting theory behind it that shows that in some ways it's equivalent to sampling a variety of different network topologies and has some characteristics that are similar to what you would get, even though in the end you only have one network. The training ends up being similar to what you would get if you actually had a whole bunch of different networks that were missing different subsets of units. Train them like you would train a decision forest, train all these networks, and then let them vote on the answer. So there's some theory that shows that dropout is doing an operation very similar in the end to what you would get from an ensemble average of training many different slightly pruned networks. Okay, so there are a bunch of things, and unfortunately we're not spending enough. This is a course on we're not going to have enough time to spend on all these. So in fact, if you're interested, there's a nice course on optimization methods I recommend. Okay, so to summarize gradient descent then, here are things that you should have gotten from the discussion so far. It's updating every one of the network parameters simultaneously on each iteration of gradient descent. It's easy to generalize it to arbitrary directed acyclic graphs. You saw how we just used the chain rule to calculate the derivatives we need. I'm sure if I gave you a different directed acyclic graph, you could derive through the chain rule the derivatives you need for that. It finds the local minimum of the cost function, not necessarily the global minimum. And also it finds the local minimum over the training examples. It may or may not generalize well. It might overfit those examples. Also, it takes a long time. So for networks that people use commercially these days, or the ones that people use if they're competing for the best speech recognition algorithm or the best computer vision algorithm, some of those networks have over 100 layers. And they can take literally weeks to train. One side effect of that is that there are a number of large-scale networks whose weights you can download on the web, because people realize how important it is to have those weights. And so you can go on the web and download a set of weights for a fairly complicated deep network for computer vision object recognition. And then you can maybe modify it to retrain it on your own images. In fact, there's a paper that came out in Nature, a very respected journal, this spring, on applying neural networks to a medical diagnosis problem of skin cancer detection. The input to the network is an image of a blemish on somebody's skin, and the output is trained to do the correct diagnosis of that blemish. It turned out the network outperformed top dermatologists, and it turns out the way they trained it is they had 129,000 labeled examples of skin blemishes and the ground truth about what the disease was. But they started with a network that was trained on the ImageNet dataset for generic image recognition that was trained on over 1 million images of generic images and the objects that were in those images. What they did was they downloaded the weights for that network, and then they froze them all, or maybe they didn't freeze them, I can't remember. They added a new layer to the output. Basically, they replaced the last layer or two of that network and then trained it on the 129,000 examples they had. So it's really remarkable. And what was going on there, the reason it worked so well, is that a lot of what that first network had learned was information about lighting variations, that how the same thing would look under different lighting variations, or if it appeared to the right or left of where it was in a previous image. So translation invariance, rotation invariance, scaling invariance. If the camera's closer or further, it looks bigger or smaller. And that network that was trained on 1 million regular images had built up sets of features that were invariant to those irrelevant things when it comes to classifying the objects in the scene. And those same physical lighting variations, scale variations, translation variations happen in the dermatological images, in the skin cancer images. And so the network had already learned the complicated task of trying to be invariant to those kind of variations. So, yes?
So it's just the concept of transfer learning? Is that what?
That's right. So some people would call this transfer learning, where you're interested in task 1, but you have a whole lot of data for task 2, which is somehow related. So you use that data for task 2 and then try to learn something that can be modified by the data you have for task 1. So this is exactly that. Okay. But the good news is, even though it takes forever to train these things, applying them is not usually such a problem. Why? Because all we had to do to apply the network to a new input, in our case, was just a matrix multiplication per layer. So even if I have a 100-layer network, I do 100 matrix multiplications. If I do that on the right hardware, like a graphics processing unit, it can be very fast. The reason training is slow is that it can take hundreds of thousands or millions of iterations of gradient descent to get to the right place, to the right set of parameters. But after you've trained it, then applying it, you only, of course, just do one evaluation of the network. Okay, so moving along, I want to jump across some slides, which we'll cover next time, and talk about a different kind of deep network than we've seen so far. This is the kind of network that is almost always used for image classification. And it's the kind that you're going to be looking at in the homework that came out this week and the programming assignment that comes out next week, where you're going to get a chance to actually work with a convolutional neural network for image analysis. Okay, so remember this picture from the previous lecture. Neural networks really are responsible for dramatic advances in computer vision. But to get to those advances, they had to deal with some of these issues. We were just talking about some of these issues in the context of skin, pictures of your skin. But, you know, even in pictures of anything, there are things like translation and lighting and scaling changes that are really irrelevant to what you might be interested in classifying, but occur all the time. Also, manual engineering of the low-level features is painful. And as I mentioned last lecture, the reason that this dramatic progress has happened is because neural nets just cross this whole idea out. And they just work directly on the input pixels of the image. And they learn the low-level features that they're going to use for classifying the images, unlike earlier approaches where humans were trying to figure out what would be good features like edge detectors and things like that. Okay, so let's look at an example of a convolutional network. Here's one that classifies, and this is the one you'll be working with in the homework. This one takes a 32 by 32 input image, and it's an image like this of a handwritten character. In fact, the data set we'll be using in the homework, these are digits from 0 to 9. But they're written by different people, and they don't all look the same. And the job is to figure out which of the 10 input, what are the probability to assign to each of the 10 possible digits, 0 through 9. And we'll use the softmax, which is just the generalization of the logistic function, to train so that those 10 outputs correspond to the 10 probabilities we want to assign to the 10 candidate labels. Okay, so now what is a convolutional neural network? What it does is it's an architecture that looks like this. Some of these things are familiar to us already, like it ends with some layers of fully connected sigmoid or rectilinear units, just like we've been working with. But before that, it has generally stages of convolutional layers and max pool layers. And it starts with, in this picture, 32 by 32 array of pixel values, and it learns sets of features that get that essentially create arrays of features at lower resolution. So, for example, at this layer of the network, we have 16 different arrays that summarize information about that input image in 16 different ways. But each of those arrays is itself a 5 by 5. So you can think of, we drew our networks before as just a vector of hidden units at each layer. But of course, we could have wrapped that vector in some way into a matrix. There's no real difference. Just, you can code any matrix. It's a vector. Just run a raster scan on it, or row major order, or something like that. Okay, so one thing that is interesting about convolutional net architectures is that they quite often calculate not just one channel of information, but multiple channels. So here we have 6 different channels of information, each one summarizing a grid of information about this grid of initial pixels. But in in this case, 6 different ways, and they're only 28 by 28. Okay, so the overall architecture tends to go from big pixel set to smaller and smaller summaries of those that are increasingly complex functions of the input. And as I said, we already know these two kinds of layers, sigmoid and rectilinear units and softmax. What we haven't really talked about is max pooling convolution layers. So I want to go through that. Here's what a convolution layer is. It is, here's our input image, and the first convolution layer in the network works like this. It has a bunch of output units for that layer, but each output unit, like this red square, is a function not of the whole image, but just of some subset of the image. Okay, so this is not a fully connected network. Instead, each of the output will look at a slightly different subset of the input pixels. So if this is our input image that has, you know, height h pixels and width w pixels, in this network, each unit at the output of this layer will look at a k by k grid square subset of those pixels. And then it'll output a value, which is simply a matrix called K times element-wise times the subgrid that it's looking at. So put another way, the output of that unit is going to be itself a grid, right? But the ijth element in its output is going to be just the sum over over the height and width of the K grid, which is m by n, of the input image sub I plus m times the mth element of K. So it's a little easier to think about it in the following simple diagram. If this is my input image up here with 12 pixels, A through L, and my K matrix, it's called K because some people call it a kernel filter. It's terminology, it doesn't matter. But if my K matrix is this 2 by 2 subgrid, then the output of that layer is going to be the element-wise product of the kernel times the little patch that we have in the top left. And so it'll be the element A times the corresponding entry in the kernel matrix, W, and then plus, it's the sum of all these element-wise products, plus B, the next one over, times the next one over, which is X, plus EY plus FC. So it's just a weighted linear sum of the different weights in the kernel matrix times the corresponding pixels on the input. Okay, and since we want a grid of outputs, this is just the output for the top left corner of that grid that we're outputting. The next one over, we have to do another computation. In this case, we use the same kernel matrix, but we now apply it to the grid just shifted over one. And then shift it over again one, and oh, we can't shift it any further because we'll fall off the end of the image. So even though the image is 4 by 3, this is really only 3 by 2, right? Because you can't apply the kernel if it falls off the end. Okay, so the way I think of this, actually this is a very good way to think about it. It's equivalent to the following thing. It was like, what if we said we wanted to train a different unit on each 2 by 2 subgrid up there, In a way, that's what we're doing, except what we're doing is we're saying each of those, we'd still have 3 by 2 units if we did that. The difference here is that those 6 units are sharing the same weight parameters. So there's really only one kernel matrix, and it's getting used every single place that the kernel is being applied. So it's like training 6 units, but their weights are all tied together. And in fact, that's exactly what happens during training. During training, what you do is the equivalent of pretending that these are 6 different units, figuring out the gradients with respect to each one, and then summing them, because in fact it's just one set of parameters, the kernel matrix, and that's how you get the derivatives. Okay, so it's actually a very simple idea. That's the whole idea of convolutional layers. And you see what it does is it builds in, by design, a kind of translation invariance. So now if we're trying to learn to recognize Hillary's face in a photograph, and sometimes she's here and sometimes she's over here, this kernel matrix is just the kind of thing we want to build into our architecture. Because if it learns W, X, Y, and Z as a good detector of Hillary's face, then it's going to be applying that same detector everywhere in the image. It's doing the scan of the image, looking for whatever feature it's recognizing. It's looking for it everywhere. And it's outputting an array, 3 by 2 array, of values that correspond to applying the same kernel filter matrix, but just scanned across the image. So that's the idea. The formula is very simple. You just sum over the number of rows and columns in the kernel filter, multiplying the corresponding image pixel by the mth value of the K-matrix. And when you train the network, of course, these are the parameters that are going to get trained. But the nice thing is when you train the network, those parameters are going to get a lot of training data. Because for every training example you give it, every image you give it to train on, it's going to get 6 different training examples of what it should be doing. And so there's a kind of a key to the success of these convolutional neural networks is they effectively don't have that many parameters in them, a single layer like this. Like if you build literally a 2 by 2 kernel matrix and you run it over a 1,000 by 1,000 image, there's still only 4 parameters that you're learning. Even though you're getting 1,000 minus 3, whatever, I can't do the arithmetic in my head. You're getting a lot of instantiations of where that kernel can lie on the picture, but it's still only 4 parameters that you have to learn, so you get a lot of information. Okay, so that's the idea of a convolution layer. The other kind of layer I mentioned is a max pool layer. That's even easier. Again, we have a grid, and we're going to move it around. But now the output of the max pool layer is simply the maximum of the values it's looking at. So it's the maximum of the pool. Now, why would you do such a thing? It's another kind of smoothing or translation invariance. Like suppose in one training example, it's location E where the important edge is to tell you what kind of skin cancer it is. But in another image, it's actually moved over to F. Then by taking the max of that pool, A, B, E, F, as the output of this layer, you're just kind of saying, I'm letting things jiggle around a little bit and I'm not worrying about it. Okay, so I think of convolution and max pooling as kinds of units, kinds of layers that are very, very appropriate for photographic image analysis. because they kind of build into the architecture this way of dealing with translation invariance and actually scaling invariance too, although we haven't said anything that makes it clear why that would be the case. The reason that's the case is look how the network actually is built. First, there's a convolutional layer. This convolutional layer uses a single kernel matrix, however big that is. Well, it's outputting a 28 by 28 feature map, so you can figure out the size of this, but it's probably on the order of 4 by 4 or 5 by 5 or something like that. It's just learning that many parameters for this entire array of output values. And there's a different kernel matrix for this second one and a different one for the third one. In fact, it has 6 different feature maps that it's learning based on just 6 different kernels. The next one is doing a max pool. So what that's doing is it's looking, as we said, at a subregion of this feature map and just outputting the maximum value that it finds. Okay, so if the kernel matrix up here found a signal that looks like an important edge in the skin photograph, then this thing is giving us a lower resolution 14 by 14 feature map instead of 28 by 28. But it's giving the full feature value of the maximum of those feature values as its value. So it's a lower resolution, but still, if the feature's there, it's going to weight it just as heavily as this one did. But now look what. We do another convolution on that, and another max pool after that. So this helps with scale invariance. Because imagine in one photograph we have Hillary right up by the lens of the camera, so her face is really big. But in another photograph, she's very far away, and we have to look. It's a very small scale photograph. Well, if she's far away, then maybe this will be able to learn to be a Hillary detector. But if she's close, there's no way this will be able to be a Hillary detector. But on the other hand, once we collapse things, then this is effectively looking at a bigger fraction of the information in the image. So this is dealing with larger scale subregions than this one is dealing with. And so by having these alternate layers of convolutions and max pools, we give different stages in the network an opportunity to find things at different scales. Okay, so you can think of all these initial stages as doing that. And then we have this is basically a 2-layer fully connected neural network with output softmax to turn those extracted features into the classification 1 out of 10 probabilities. Yes?
What determines the number of feature maps you would like to have?
What determines the number of feature maps you would like to have? Sadly, experimentation. So this is very much an art and not a science. And in fact, if you read the reading that's on our website, the chapter on convolutional neural nets, you'll see they describe a variety of architectures and how those vary. And people are still developing alternative architectures and trying hard to improve on what's there. And a lot of the exploration is basically at this level. What should be the combination of types of layers, number of alternative channels? There's a lot of experimentation. Yes?
How to design the kernel matrix?
How
to determine the kernel?
Oh, how do you determine the kernel matrix? The only thing you have to determine is the size of the kernel matrix. The values that are in the kernel matrix, that's what gradient descent is giving us. Exactly the same as it gave us those matrices of parameters in the network that we trained at the beginning of class. So what gets learned here and what's fixed is effectively the architecture, the sizes of the kernel matrices, the sizes of these feature maps. Those are all chosen in advance by the designer. And then the only thing that get learned are the parameters of the kernel matrices. Nothing gets learned here. You fix ahead of time how big a region you're going to max pool from. These convolutions also have kernel matrices to learn. And then, again, this max pool is just fixed. But now we have all these 120 long vector of inputs, fully connected to another layer of 84 hidden units, fully connected to the 10 softmax outputs. So there are a lot of parameters here getting learned. But basically, that's what's learned are just the parameters, and what's fixed is everything else. Okay, let's look at a couple. I like this picture. It comes out of the reading, the Goodfellow reading. The important thing to look at is this picture on the right. The picture on the right, as the caption says, are the learned convolutional kernels learned at the first layer of a supervised convolutional max-out network. That is, it does the convolution layer followed by the max pool layer. And so each of these, like this big, is one of those learned kernel matrices in the first stage of the convolution. But interestingly, neighboring pairs of these filters drive the same max-out unit. So let's think about what that means. If we go back here, what it means is the neighboring images on that next slide come from things that drive the same max-out unit. So they're the max out unit the max pool unit is going to just take the maximum of any of the features that go into it. There might be one here, and there might be another one here, and it's going to, I'm sorry, I should point here when I point to the max pool. It's going to look at all the ones that feed into here, which will be a variety of regions that are neighboring in the image here. They'll map into here, and then the max pool is going to take just what the maximum value is. And so now let's go back and look at that picture. What you see, for example, is, like here are neighboring ones. These are the learned kernels at the convolution layer that are nearby in the image. And the max pool is going to take the multiplication of this image times the subregion of the input image to get a value, and it's going to take this one too, and it's just going to take the maximum of those two values after it takes the product, right? It's going to do the multiplication of each of these kernels to nearby parts of the image, and then it's just going to take the maximum of them as its output. So in some sense, this tells you something about the regularity in the image, and so I find it very interesting. So like, here's something where, obviously this is a kind of edge detector, but the slope of the edge is a little different here than in its neighboring part of the image. And the max pool layer is going to output whatever of those two types of edge detectors reports the biggest value. So you can kind of see how this proximity and increasing scaling adds up to learning very interesting sets of features. All right, so I think that's what I wanted to say for today. Again, I think the key things you should know are kind of here. And I urge you to do the reading if you haven't. And I hope the homework is going to be a little bit of work, but I think you're going to learn a lot. And just think of the glory of your future interview. Thank you.